isn't it?
Hey, how are you guys doing?
Good. Hey,
Did
Sandeep,
any
sorry, go ahead.
did anything move on the project?
Uh, no, I mean, I'm not sure what that was about, but one quick question. Last times, I mean, I was going through the recording. Did you check it in the notebook?
I did.
No, you checked in, I mean, as per our date 16th, but you didn't check in for 17th. The one with multiple thing, I couldn't see it.
Okay.
I was trying to get some code. I don't know
Um,
if I missed it, but
let me see. Let me see. So, so one is our this one, correct? Git status and
yeah, August 17th.
oh,
No, this you modified gradient descent. That was there, but I think the August 17 one also needs to be checked in because that was the one which had some examples.
no, I think what I did was there. I think I just modified the August 17. Yeah. Yeah, this I forgot to add this one. Oh, sorry.
No, I mean yesterday only I was going through the recording, and I was trying to figure out if I can do that. And I have one question on the last time's lecture. I mean, before we start today's lecture. Um, so you were talking about, you were talking about creating our own loss functions,
Yes,
right?
yes, yes,
But I mean, loss function is basically the difference between what you are predicting and what actual value is, correct?
yes,
So then why do we need different loss functions? Because once we have a loss function which gives us more accurate, difference between the predicted and the actual values, can't we use the same loss function for almost every problem? Because at the end of the day, we are looking at the gap between predicted and the actual, right? Why do
yeah,
we need uh, um, custom loss functions or different loss functions? You
right,
getting my
right.
point?
Yeah, yeah, yeah. So, think of this way that as long as it's a single value, it all looks okay, right? I'll come back to that also. Okay. So, okay.
Sorry, when you mean single value of y?
Uh, single
Okay,
value we are trying to predict. It's a very good
okay.
question. I want everybody to join and I can give an overview. I know that it's early when we talk about machine learning, but it's not never too early. I'll like to make sure that whatever I talk about is something that everybody is getting. Okay, I'll try to avoid jargons. I'll try to keep all the words very clear. This is a very important question. Right. Very, very important question. I'll just connect my iPad as well. Why it's not charging? Not charge. It's still not charging. I set with 1%. And it's about to die. How should I movement? Not good. Good. I'm sorry, guys. Just give me a moment. My stuff is not yet charged. not charging. So let me go back one step. I'm not able to locate my. I forgot to connect my iPad and it has discharged completely. Okay, so I'm joining the meeting from the iPad again. And good.
Recording in progress.
Okay, now I'm all set. Okay, so it's a very important question. Is everybody in? 25 people. Okay, all right. You guys can see my screen?
Yes.
Okay, so the question is, okay, today is August 23. Okay, and yeah, so the question that I'm trying to answer is why do we need different loss functions? Okay. All right. All right. Now, this is a very important question, and it's a very, very, very important question. Okay. So when we talk about machine learning is nothing but an optimization problem, correct? We try to learn from the past, okay, and predict the future. And how do we learn from the past? By basically coming up with some mathematical equation with some weights, which we want to predict that this is my mathematical equation or this is my weight, these are my weights, and such that that fits into the data. And how do we say that it is fitting into the data? By minimizing certain kind of a loss. Okay. Like, for example, say this is my data, right? This is my data. Okay. And this is my line. Okay. So this is one of the strategy would be that, okay, 1 point, 2 point, 3 point, 4 point, 5 point. This is my data. This is the value that we are predicting. This is the input that we are giving. And what we want to do is, given a value of X, we should be able to predict Y. Okay. Now, the question is, how should we approach the problem? The way we had been approaching the problem is by defining a good line that goes through this data. Okay, trying to fit a line into it. And in case we see that, okay, it might be x square or some kind of thing, we basically plot another graph where we do the x square on x-axis and there is y and we come up with the weight. Okay, now somebody might say that, hey, this is not very good. Instead, what we will do is we will try to fit two lines. Okay, we will say we will fit two lines. Okay, somebody came up with this clever idea. He said, fitting one line doesn't make sense. Instead of fitting one line, we fit two lines. Okay, we fit a street. Okay, now we have two parameters to minimize. One is called the width of this street, okay, and second is called what? Second is called the error, okay, that these points should not be outside of this street, or the distance between the central line, and this. So now we are optimizing two things. One, the width of this thing should be minimum, and this data should be closest to the center line, right? So we got two loss functions, two things we got two objectives, okay? We got two objectives. One, the width of this thing should be small, and the second objective is that this data should be very close to the center line. Correct? Are you with me?
Sorry, but here also there will be only one loss function, right? The difference between the line and the points, isn't it? No.
So right now we have two loss functions, right? One is the width of this line, and other is the distance from the center line. So there are two. Okay. So usually what we do is in the loss function, we'll say this width should be minimum plus the error should be minimum. So my loss function, now loss function has two things. One is weight, other is error. Okay. So depending upon the problem, we would come up with all our own loss functions. And creating a new loss function requires a lot of deep thinking, lot of working, and usually most of the researchers end up creating their loss functions. Okay. But engineering situations you may not see. Okay. Yeah, go ahead. Somebody has raised their hand.
Yeah. Sandeep. Yeah. Sorry, I think I lost. I think there was some maybe network connectivity issue. But what are these two lines? So I understood the first line, but the two other lines that you drew.
Yeah. So this is called support vector machines. Okay. Don't worry about the term. Okay. The thing is, to solve or learn from data, there could be many strategies. One strategy we have followed was linear regression one, where we fit the single line into it. Okay. Somebody came up with the idea. Somebody came up with a better idea. He said, I'm going to fit a lane into my data. Okay. Then he said, I'll fit two lines, one on the left-hand side, other on the right-hand side. I'll keep the distance between the two as minimum, and we'll fit the lane onto this data. Okay. And the center line of this lane is the one that is going to take the decisions. Got it?
So if I understood it right, it is like we need specific loss functions because what we want to derive from the model, right? If you want to derive a single line, or we want to derive the most accurate line to pass through all points, then whatever we are doing is correct. But if you want to create a cone, or we want to create a band, or we want to create something else, a quadrant or anything else, then the loss function would differ. So basically, the success criteria will define what the loss function is.
Yes, exactly. Exactly.
Okay, got
like
it.
For example,
no, understood.
Have you guys done the celebrity like me so far?
Yep.
You did, right? So there, this is called another example of loss function. Be with me. Okay. So the problem statement is, given the photo of a person, okay, come up with, build a model M that will convert this input data into bunch of numbers. Okay, we call that embedding. Okay, given the photo of a person, convert that photo into embeddings such that that embedding. So let's say this is my photo and this is another of my photo. Okay. And there is let's say somebody else's photo. Okay. So this is me one, let's say Sandeep's one photo, Sandeep's two photo, and this is Deepak's photo. Okay. Now come up with a model such that the embeddings of Sandeep 1 should be very nearby embeddings of Sandeep's another photo, but should be very far away from embeddings of Deepak's photo. Okay, so the task is to build a model M which can convert a photo into a bunch of numbers such that those bunch of numbers is called embedding, such that the embedding of the same person's photo should be very nearby and the photo of third person should be far away. Okay. Are you with me?
Yep.
Yes.
Okay. So basically here, this is called a triplet loss. Okay. So the innovation in face embedding was only coming up with a triplet loss strategy. Okay. It uses gradient descent. It uses all the strategies that we have studied so far. The only difference it does is it says that embedding of S1 minus embedding of S2 and the square of it minus embedding of S1 minus embedding of D1 square. Okay, so this should be minimum and this should be maximum. So one loss function that he tried was this. The difference of my embedding with another of my photos embedding minus the difference of my embedding and Deepak's embedding. That's one loss function that he tried. The other loss function he tried was first one divided by the second one. Okay, so the whole innovation about FaceNet was coming up with triplet loss. Okay, so the first earlier method that we talked about was called, what do you call that? SVM loss. We also called it hinge loss. Okay, hinge loss. And then I talked about triplet loss. Okay, so when you are designing a system or solving a complex problem, there is a chance that you will end up designing your own loss function. Okay, like in our case, as you study in classification, we wanted our model to maximize, okay, maximize true positive, okay, and it's okay, it's all right, it's okay to not give good results. Okay, it's okay to have false positives. This was one of the problems that I was trying to build, that my model should not, it's okay to classify somebody as a thief rather than dropping them. Okay, so I wanted to maximize that probability that if somebody looks like suspicious, I should catch them. And if somebody is not looking as suspicious, even if somebody is looking less suspicious, still I should catch them. But it's not okay to let them go. Okay, so I wanted to maximize recall, not precision. Okay, or I was trying to maximize the true positive, and I was okay to have false positives. Okay, and therefore I had to come up with my own loss function. Okay, so depending upon the problem, you might have to design your own loss functions. Okay.
Got it.
And yes, I mean, you have to think out of the box and you have to come up with those ideas such that you can solve real world problems. Okay, very good question. I hope everybody got the answer. Please feel free to ask any questions. I very well understand that this question is hard, specifically at this juncture. Okay, and it's completely okay to, say that, okay, I did not get anything. I did not understand what you just talked about. Okay, so feel free to ask anything.
Can you explain this again, hinge loss and triplet loss?
Yeah. Okay. So though we will study the hinge loss as part of the SVM chapter, the hinge loss. Okay. And we'll study the triplet loss as part of the computer vision. Okay. But again, okay, let's take a look at good diagrams. Okay, hinge loss. Okay. All right, not this one. Okay. All those people who are just creating this content, right? It just becomes very annoying. Specifically, like Geeks for Geeks, I don't know. Like they have gone super crazy with trying to generate all kinds of content, and I can't trust this content. I've seen like so many mistakes in that content, and that's just, it's not a good idea. It's better to just stick to this. Okay, let me see. Okay. All right. All right. Okay, let me see. Let me try drawing it if I can. Okay, so I'm talking about another loss function. We call that hinge loss. Okay, right. So we have, let's say, some data points, and somebody came up with a better idea that instead of trying to fit a line, we will fit two lines to it, such that maximum lines are within these two lines. Okay, so as far as possible, keep all the data points inside, except maybe one or two outliers could go outside these lines. Okay, so we have two objectives. Draw the two lines such that maximum number of points are within these lines. Okay, or you can say in other words, or okay, or the okay, or you can put it the other way. The width of the street or the lane is small. Okay, width of the lane is small. That is my first objective. Second objective is all the points. Ooh, what's wrong with this? Okay. Okay, all the points are close to the center of the street. Okay, so this distance that you see from the center, this distance of each of them should be as small as possible. Okay, and the width of this street should be smallest. So there are two objectives, correct? Width should be small and all the points should be closest to each other. You with me?
Yes.
So if W is the width of the lane. We can say W, the absolute value of W, plus the distance x1 minus, let's say, center line, okay, and that square next to minus center line, like that, okay, some sort of this distance. I'll come back to that. So we'll come up with the geometric formula for both of these and then add them. Now we combine the two losses, two errors in together. We want this to be smallest, we want this to be smallest, so this becomes our loss function. Okay, so it'll be tweak the slope of the lines and tweak the width of the line as much as possible, such that maximum points are lying within these two things. Got it? So this is a custom loss function. We call that SVM loss, or we call them hinge loss.
You have taken the example of classifying the photos. So why do these functions work better for classification?
No, that was a separate one. I'll come back to that one. Right? This one was for regression. Okay. So we are saying that this hinge loss would work better because it is trying to keep all the data points within the lane. Got it?
Okay.
Okay. So usually
basically, basically here we are trying to find out not the line, but how far that line can move without on both directions from the
center.
I don't know how to put it. But yeah, from the center to incorporate as much as points, all the points, isn't it?
Yeah. Yeah.
Or are we not trying to find out the deviation from the standard line actually, right? Like by
Both. We are doing that with that also.
Yep.
You're doing that also.
Sandeep, are we trying to use like the limits where maximum we can do coverage using the limit, something control limits kind of? Is it that?
Basically, here there are two objectives. One is lane should be smallest, and minimum number of points should be outside this lane. Okay, the lane should be smallest, and minimum number of points should be outside this lane. That's all we are trying to minimize. Okay. So
Even if we were to draw a single line,
mm-hmm.
even if we were to draw a single line, the objective remains the same, right? That we want to have the points as close as possible to the central line.
Correct. So these are different ways of looking at it. One way was do the x1 minus y1, predicted value minus the actual value, and do the square and sum it. Okay. But what people found is that this approach of imagine for a moment that you have, let's say, this data point. Okay. This data point. Okay. So, right now, for this, let's say somebody draws a line like this. For them, this is an outlier. Okay. And somebody can also draw a good line like this, and this is an outlier. But, okay. Okay. Now let's take a look at what will SVM kind of people do. Okay. So imagine that somebody draws a big, a big lane, right? So this lane is going to be really big. And while this lane is going to be really small. Okay. So this lane is bigger as well as, right? In order to fit all these data points into the lane, this lane is too big. This lane is fitting it. This is way smaller. And therefore, people found that this hinge loss works better than the normal mean squared error. Okay, that's what people realized after looking at many cases. Okay, so you will be using the hinge loss at many situations, but underneath, most likely you will be using the gradient descent. Okay, so the loss function is different, but the way of optimization is still the gradient descent. Got it?
Got it.
Okay, so that's the core idea. That's the core idea. The loss function would keep coming all the time. Other example I took was triplet loss. Let's take a look at triplet loss. Okay. Okay, so triplet loss is a way to, right? So let's say these are, where is it? Yeah, not this one. Wikipedia one is generally more trustworthy. Okay, triplet loss is, where is the triplet loss example? This is the one I'm talking about. This is also, okay. Yeah, triplet loss is that we basically compare, right? So imagine, okay. No, I don't like it. Let me just draw it again. Okay, imagine that you built a nice model or M model, or we want to build M model. Okay, through this, you pass my photo, my first photo, then in second time, okay, second time you pass my another photo. We get the embedding of Sandeep's first photo, embeddings of Sandeep's second photo, and the embeddings of Deepak's photo. Okay, Deepak's photo, D1, let's say. Okay, Deepak's photo. Okay. So the problem statement is that come up with that model or come up with that bunch of knobs such that these two are as close as possible, and this or this or this should be as far as possible. Okay, so tweak the knob, you tweak the knob slightly, pass all the inputs S1 first, then S2 first, then and D1. Basically 3 times you execute the model, compute by tweaking one slightly, we tweak one of the weights, observe, are these getting closer or farther, right? And how do you make it seamless? By creating a loss function such that, let's say one loss function could have been, one idea could be that my loss function is E S1 minus E S2 whole square, and then you sum the values and divide it by E S2 minus E D1 whole square. Okay, so this is my loss function. So I would tweak these knobs in this model slightly, observe, is this error going down or going up? Okay, if it is going up, I'll keep on going, twisting this knob to the other side. Otherwise, I'll twist it forward. Okay, so this is one example of the loss function. The embeddings of Sandeep's first photo, Sandeep's second photo, you subtract them, square them, this should be small and this should be biggest. Okay, this should be big, the difference between these two should be big, this should be small. And how do we express it in a single loss function? Either divide the first one by second or subtract the first one from second. We could also say embeddings of Sandeep's first photo, embeddings of second photo, and we do the square, take the sum, and then subtract embeddings of S2, embeddings of D1, and that's it. Okay, so we can compose all kinds of loss functions. It's up to us, and we observe that which of these loss function is doing a better job. Is this giving a better job, a better answer, or is this giving a better answer? And people keep on experimenting these loss functions every day. Got it?
Yeah. So in denominator, you take an ES2. It could be ES1 as well.
It could be S1 as well. Good point. Or you could come up with another way that, okay, in denominator, we will have two terms, ES1 minus ED1 whole square plus ES2 minus ED1 whole square and summation. It could be. And people have
Also, I
tried.
mean,
Yeah, go ahead.
yeah, so basically whether it is supposed to ES1 or ES2, right? That you will know only by trial and error, right? There's no definite way of finalizing something, right? You may have an idea of how you want to do it, but coming
Yeah.
up the final loss function, it will be more of trial and error, right? Or there is a better way to do it.
I'll show you. Okay. Yes. So this is true research. This trial and error that you said is the real research. Okay. The main credit of the people who designed ChatGPT today goes to the people who designed this paper called Transformers. Okay. Now, if you read the first few lines of this, okay, this is the paper behind most of the innovations. Okay. Now, here, okay, okay, if you see here that the contribution of the paper, if you see, so many people have contributed. For 8 people have contributed to this paper in which year? 2023. Okay. What? 2nd August 2023. No, it must be very old. It would be somewhere of 2015.
Yeah, 2017. I mean, some details were added in 2023, but the original is 2017.
Oh, this line was added.
2017.
Yeah, this line was added. Yeah. Okay. Yeah. Notice this. All the authors have equal contribution. The listing order is random. Jacob proposed replacing this. It started with this. Assis and Ilya designed and implemented first transfer models. Noam proposed scale.product attention. Okay. Multi-head, parameter free, and so on. Nikki designed and implemented, tuned various variants of original code base. Okay. Yeah. So where is, yeah. So what you see here is that what these guys are doing is they are experimenting with all kinds of loss functions, all kind of structures of things, and then observing which one is giving better accuracy on various data set. Okay, that's all. Okay, so I want, yeah. What?
What do you mean by attention here?
Attention is a kind of a neural network design. We'll talk about it. Okay. And the attention neural network is something that seems to work. So they did not just wake up like Ilya Raja, or one of the musicians from South India, and just wrote the music, right? He used to just write the music. Not like that. They basically experimented with various loss functions, various neural networks, various structures, various kinds of normalization techniques, and all of that, like brute forced around it. And that's the true research. Are you with me? So whether to keep both ED1 or ED2 in the denominator or not, all of that is a real research. Okay, people do that a lot. Okay, people do that a lot, and you will be surprised to see that there are so many different kind of loss functions. Okay, and like this one is simple, means squared error. The squared error instead. Okay, we call it squared error or squared loss. And are there more? I wanted to show you if we can.
Sandeep, one second. Sandeep, can you hear me?
Yes.
In the triplet loss, right?
Yeah.
Can you please explain me how did we get that ED1? Can you please repeat it again?
Okay. So it's basically this, right? So Here is the idea. Okay, so this is the photo of Sandeep's first photo. Okay. Okay, what we did was we said, okay, we will get, let's say, 50 weights here, 50 weights. Okay, we'll just arrange these 50 weights. Took your photo, right? Took your photo, multiplied with these weights, and put first value in the output. Then took your second pixel and then multiplied with these things and then outputted this. Okay, so you can think of it that we are multiplying, dividing, or doing some mathematical operation on your photo and converting your photo into a bunch of numbers. Initially, these embeddings do not make any sense. This model is a piece of garbage initially because these weights are just random. So it gives some random value. Fine. Now what we do, we take your first photo, feed to it. It gives us some embeddings, garbage. Then my second photo, it produces garbage embeddings. Okay. And then we take Deepak's photo, and then it again produces the third bunch of numbers. All three are just garbage initially, because all the numbers that we are multiplying, dividing, and squaring and doing all the mathematical operation on the photo to produce this result, all of these things are random right now. Okay, so right now we gave the three photos, it produced these three values. Okay, then what we did was, we slowly tweaked one of the parameters, one of the knobs slightly, and observed, did ES1 and ES2 move closer and moved away from ED1 or not? If we did, we kept on moving it. And that way we kept on tweaking these knobs until ES1 minus ES2 is small and ES2 minus ED1 is bigger. Okay, this is just random triplet loss I've written. Okay, this difference square divided by this difference square. Okay, and we kept on repeating this process over and over on all kinds of photos of all the people. And once after a while, the system figures out how to convert photo into bunch of numbers such that if you present same person's two photos, it will tell them that they are close by. Got it?
Right, sir. Thank you. Yes.
Yeah.
Is there a manual verification on those photos whether these embeddings are correct or not?
No, no manual. Only the loss function and the gradient is doing all the magic for you.
Now for training, for example, let's say initially you said garbage, right? First two are garbage.
Yeah,
how do we know they're garbage?
Yeah. So basically, no, I mean, initially they will be garbage because we have just chosen these mathematical function randomly, all the weights to be randomly, correct? And then what we did was, the only manual work here is to prepare this triplet data set. Okay, all we did was we gathered from the LinkedIn profiles different photos of the same person and one random photo of some other person. Okay, that's all we did. Okay, and we kept on training it continuously until we hit upon the same like we basically keep on tweaking in and until as long as the loss is going down, we keep on doing it until the loss is going down. That's all. Is everybody
so we had a training data that we already knew that this is the right classification or not?
No, we had training data which contained, let's say the training data was that I had two photos of Sandeep, I had two photos of Deepak, I had two photos of Vishnu, I had two photos of Subodh, right? And then what I did was I got Sandeep's two photos, I picked one Deepak's photo, for 2 photos of Deepak, I gave Sandeep's photo. So I created these triplets. So I created 3 triplet groups. Okay. And then basically I fed these 3 photos to the model. Model converted them to embedding. Then we kept on tweaking them. Okay.
Okay.
And
as an example, if we are using RGB to represent photos, we are multiplying RGB values by some number, right?
yes, yes, yes.
Okay.
Yeah. There are some structures of the way we strategize multiplying. We call that convolution neural network. Okay. We did that. I wanted to keep the terminology away for now, but you will get that idea very quickly when we talk about it. So yes, we are on the same page. So we kind of multiplied those RGB values, summed up, and did again and again. And we had, let's say, 5,000 such bunch of numbers or weights, not 5,000, say 5 million such weights. And we basically keep on retraining it on millions of photos. And there we have the FaceNet model. Okay.
Okay. Thank you.
Yeah. And I think for FaceNet only, the Turing Award was given. Okay. Turing, the Nobel one was given for FaceNet, the image recognition system. Is everybody with me?
Yes.
Okay. I just wonder, like, how come Turing Award is not given to the authors of GPT? Because it has actually passed the GPT, Turing test, isn't it? Interesting. Okay. Yeah. So yes, we are not going all over the place. It's a very good question. And was I able to explain? That's my question to all. Was I able to bring everybody on the same page? No? Yes?
Yes.
Yes.
Yes, I mean my question of why we need multiple or custom loss function, I think I get a very clear picture of why it is. It's not, I mean, as important the model is, similarly the loss function is equally important.
Yeah. Yeah. Okay.
So
And
one quick question. Do we also have some research available that which kind of problems will work best with which loss functions?
which kind of
Problems. Which kind of problems that we are trying to solve?
yeah. Like for example, right, if you are solving regression, okay, usually you would go with hinge loss, triplet loss, and so on. Okay, right? And then right, if you're doing classification, okay, what is the difference between classification and regression? In regression, we try to predict a value, like given all the parameters of a house, predict its value. Given the parameters of a car, like how old is it and so on, predict the car's value. Okay, please note that classification and regression both are a supervised machine learning problem. What's a supervised machine learning problem? A machine learning problem in which you are given labels. Labels as in there is some amount of training data available. Labels specifically, like for example, given a photo of a vegetable, predict what is there in the photo, whether it's apple or bananas. Okay, so apple or bananas is called the class or the label. Okay, it's basically single label, and it could be either apple or banana. The input is a photo. Okay, now this this data set has, the training data set would have labels saying this photo is apple, this photo is bananas. Okay, so you have, if you have labeled training data available, we call this problem to be a supervised machine learning problem. Okay. On the other hand, if the problem statement is like this, given these 5,000 images, can you put them into 5 buckets such that each bucket have similar images in it? So this is a unsupervised problem, unsupervised machine learning problem, because nobody has given us this data that which photo belongs to which bucket. Okay, so there are unsupervised machine learning problem and there are supervised machine learning problem. Now, in under
Google Photos, sorry,
Mhm.
the Google Photos that we have, does it use supervised or unsupervised? Because it does not know those photos in advance, right?
Yeah, so the model that has been trained is maybe that was trained using supervised data. Okay, and yeah, so that is okay. Now, usually problems that the way you will solve is you will solve the problem by the way of first unsupervised and then supervised. Like for example, instead of labeling all the photos in Google Photos, what will I do? I would just group the photos such that they look similar to each other using some algorithm. And then I would label each group, and that will be quicker for me. Okay, so usually the cleverest job of a machine learning engineer is convert a problem, mammoth problem, into unsupervised machine learning problem. Okay, and solve it. Like for example, GPT. Like GPT, nobody actually wrote all the questions and all the answers. Instead, what people did was they took all the articles from Wikipedia, all the internet, and we just built a system which predicts the next word. Okay, so from unsupervised data, we created a supervised machine learning problem. Okay, by generating the labels. Label is nothing but next word to predict. Okay, so supervised and unsupervised, I hope everybody is clear. It's in simple words, if the data has labels, training data has labels, we call that supervised problems. Otherwise, we call it unsupervised if it doesn't have the targets or labels. Okay.
So Sandeep, the labeling of the data, so that will be a generally a manual exercise, right? Where a large set of humans will kind of label it.
Ye-
Like for example, if we see these CT scans or any X-rays, right?
Yeah.
So then someone has to annotate it. So that is like someone has to label it, correct?
Yes. Yes.
So Sandeep, is it not that we always have to start with supervised? Because if there's an algorithm that we want to use for unsupervised, that algorithm has to be designed using supervised only.
No, so usually, like, how do you learn? How did you learn? Supervised or unsupervised? You.
I think supervised. Because somebody, let's say I am a child, I have some new object, right? So somebody has to tell me the name, that this
Okay.
is what it is called, right?
Okay.
So that is the supervised part. Later on, I can say maybe similar objects and identify and say, okay, because I had learned using supervised, now I can look at all of these and say, this is what it is called, or this is what is called something else.
See, sense of gravity, sense of balancing, sense of walking, sense of touch, all of that you learned in unsupervised way. The people who are, right, like everyone, the way a child explores the world when they're playing around with slippers, right? My kid used to play around with slippers, okay, and bathroom slippers. And the reason that they are doing is they are learning in an unsupervised fashion, okay? Because your parents did not provide you this much data. Okay. And yeah, so you did not learn in a supervised fashion, and you learned in an unsupervised fashion. Almost everybody, except for reading, writing, and the rest of the education, and probably like even let's say learning a language. The way we have learned the language is not like nobody can learn language by memorizing dictionary. We learn the language by interacting and listening and interacting and listening. Okay. So, right, for example, you did not understand the meaning of a word because somebody told you as is. Okay. You learned the meaning of a word by associating, in what circumstance when it was spoken, how it was spoken. So you learned it in a unsupervised fashion. And that's the most powerful thing. If you think about even animals like dogs and cats, they learn in unsupervised fashion. So we learned in unsupervised, and that's the holy grail of entire machine learning. If we could design a system in which we can do the unsupervised, and there are like lots and lots of research, we'll talk about this as we go ahead, that what we do is we take the photo of a person, cut the corner or half of it, and let the machine reproduce it. Okay? Or take the photo of a person and just color it to make it black and white. Now, black and white is your input, colored is your output, and let the model learn to paint. So we make the model learn to paint the picture by trying to, we have by creating the labels very creatively, like, and lots of magic goes into this. How can I convert an unsupervised learning problem into supervised? Okay, because gradient descent needs loss function, right? We need target, and we need a loss function, and therefore we need to convert all kinds of problems into all unsupervised problems into supervised problems by generating labels. Okay, and that's a very tricky game. One of the techniques that people used was take all the data from Wikipedia, take each word from each sentence, just take one word at a time and delete it. Okay, and ask the language model to try to fill in the blank. Okay, so that was before ChatGPT. Okay, so before ChatGPT, people had been trying to do that. Okay, and those who modeled the previous BERT was essentially that. Okay, am I on the same page? No.
Yep. No, I'm getting the point actually. Yeah.
Yeah. So if you think about it, the whole holy grail of AI or machine learning is, how can I make the machine learn by itself so that I don't have to teach? Okay.
Yep.
ChatGPT wouldn't be smarter than people if we were teaching it, if we were generating labels for each
Yep.
question. Okay. The magic was we kept on feeding it data and let it predict the next word, and there it learned to predict the next word, and it can now give great answers, right? So yeah, so
Yep.
the whole magic is converting the unsupervised machine learning problem into supervised. Okay,
Yeah.
and that's the magic. So yeah, I hope everybody's clear. Supervised, you have label data set. Unsupervised, no labels. Okay. Supervised could be regression, where we are trying to predict a value like house value, car value, how tall will be the person, what will the weight. So when we are predicting a numeric value, that's regression. Okay. Now, classification is about classifying into one of the classes, good, bad, and like classifying into A, B, C, like MCQs. Okay, that's called classification. Okay, now here is a trivia for all. Question: Is ChatGPT supervised or unsupervised?
Unsupervised.
Okay, so it is started as unsupervised, but then it is both. Okay, answer is both. First, unsupervised, and then supervised. And usually such kind of things, people call them self-supervised. Okay. All right. So now the next question is, if this is supervised, if ChatGPT is supervised, is it classification or regression?
It is regression
Regression.
because
What
it's
does it
trying to
mean?
figure out it is trying to figure out the next word, right?
Yes.
So
Yeah.
And word is not a number. Word is not a decimal number.
no, it is trying to get the closest attribution. No, I forgot the word which you use. I mean, yeah, I mean every word is a number for ChatGPT, right? It's trying to predict the one which is nearest to what come next.
Okay, now let me surprise you. It is
the pattern.
I think it's a
Yeah.
classification earlier, then it's regression.
It was classification.
Then, but Sandeep, how is it supervised? Because it's auto learning, right? I mean, like from all
No,
the
so
content
the
available
way
on the internet.
no. So we converted that content, right, into input and next word, input and next word. Like, okay, we break it down, the problem, into input and output. So what kind of data do we feed to ChatGPT is this, okay? What we feed is, I can just show you this nice presentation that I did. Okay. I hope you wouldn't mind. I think it's okay right now. All right. Don't worry. Okay. This was my last presentation. Okay. I was giving to the Pan IIT here. Remove it. Now, I think I removed the main important aspect from it. Yeah, this is okay. So we know, so far we learned it this way, right? That basically the way machine learns is we have the input and it predicts the output, and these are knobs. We train the knobs, we tweak these knobs to get the expected output, correct? We multiply these numbers over and over. That's all. Now, we basically, right? So for ChatGPT, what people did was they took a big sentence and broke it into input and output pair. For example, if the sentence was, remember that whatever your heart, we broke it into prefix and the next one. So ChatGPT would predict all kinds of words and we will beat it till it says heart. Okay, we'll tweak these knobs to make it say heart. When the input is this, we'll tweak this. Yeah.
This is supervised, right? Because you are giving a label.
Yes, so we extracted labels from a continuous text. Okay, so we basically converted the whole paragraph into these pair of words. So the actual sentence was, remember that wherever your heart is, you will find treasure. Okay, so first we gave, remember that wherever your heart is, you will find treasure. We also said, remember that wherever your heart is, you will find. So find is the target here, and this is the input. Okay, so we beat it. We kind of tweak these knobs. We kind of do the gradient descent until it starts saying find. Until it starts saying will in this case. Until it starts saying you. Until it starts saying is. Until it starts saying heart. And that's it. Okay. So
You
basically,
mentioned that activity started as unsupervised, right? But
this is
here,
so this is the
but here you are
unsupervised.
telling the output, right?
This
You are
was the
telling that
unsupervised text. This was the unsupervised text. We translated into a supervised problem. Got
no,
it?
but you're telling the system that
But then,
heart is the right word or not, right?
Yeah,
So that means you're creating a label.
correct. So this
So does
we
it not make it
converted.
supervised?
We converted the unsupervised problem into supervised. That was the tactical part.
but then this way, Sandeep, there would be infinite number of permutation combinations, right? Like, I mean, I know there would be some logic, some algorithm, but to a layman, mean this is like a one regular sentence, and now there
Yeah.
would be such infinite combination permutations available in the
Yes.
world, right? Then how
Yes.
are you going to supervise every sentence or whatever?
I mean, I don't think there will be infinite, right? There will be
There will be
very
fine.
large number of,
I
there
mean,
will be finite
infinite,
number of combination. No,
See, these
finite,
are
I'm
not
saying
random
that it won't
sentences.
be,
very,
These are
very
the
large.
sentences.
it is,
These are the sentences from Wikipedia, New York Times, from the whole internet, and so on. So it is not
so it
infinite.
is,
It is not
yeah,
infinite,
it
but
will
there
be,
will be a very large number, I mean.
Yeah.
that's the reason why they take
Yes.
so much money for one query.
That's
But
the reason Nvidia's stocks are going up.
no,
Yeah.
okay.
Yeah. So yes, that's the reason you need lots of GPUs, lots of machines, lots of computing, and that's the reason they made lots of money. It's a hard problem. It's a fairly hard problem. Okay. That's why only few players dare to get into that. Okay. But yeah, this is a good problem, but it's and the knob's positions are not infinite. We are doing the gradient descent there. We tweak the knob slowly, observe, is it giving heart or not? If it's not, then we keep on tweaking it. Is it getting closer to heart? Yes or no? And then we keep on doing that over and over and over. Okay.
But
All right.
in this scenario, sorry, this last question. So in this scenario, what will be the tweaking? I mean, how will you, I mean, what will you tweak? It's not an equation, right? So it's like
You have to convert this into equation. Okay. Okay. Let me put it this way. Treasure as a word, okay, is represented by 10,000 numbers. Okay. If your dictionary has 10,000 numbers, treasure will be at one of the positions will be 1 and rest of the numbers will be 0. So treasure is an array of numbers where all numbers are 0, all words are 0, and only treasure is on. Okay. So your model is producing 10,000 numbers. It's producing 10,000 numbers, and you're comparing which one is matching the target. So we are basically tweaking it. Okay. So each word is represented by an array of 10,000 numbers, where this whole array is filled with zeros except for one word. That's all. Like if you had in the dictionary, let's say your dictionary had only A, B, C, D word. So, and we will say 1, 0, 0, 0. Okay. And B will say 0, 1, 0, 0. C would be 0, 0, 1, 0. D would be 0, 0, 0, 1. Got it? This. You see that? So like that, for each word, if you have 10,000, the dictionary size is 10,000, then you'll have 10,000 array, and that's it. We call that one hot end. Okay. So we
What we
convert
call, Sandeep? Sandeep, what's the word you mentioned? What we call
one hot encoding.
one hot encoding. Okay.
Yeah. All right. I know I'm skipping a lot ahead, but it's completely worth your time. Okay.
And Sandeep, can I ask a question actually here? Like, you remember, right, with Chat GPT early days, or when version 3.0 or lower were they, like it used to generate a lot of false information. Now that, I mean, percentage wise, that false information is now a lot lesser. People, I mean, 4.0 is generating a lot more accurate information than ChatGPT previous version. So, like,
Yeah.
how did they manage to get it all right? Actually,
They
Do
basically
they?
explained it. I think they gathered lots of question answers from here and there. Also, the human annotated lots and lots of questions. And they basically, there are like lots and lots of techniques. So one of the technique was that they worked really well on, they created parallel model who will be the teacher. And this will be
Okay.
the model. And they both are competing against each other. Okay. So there are lots and lots of interesting ideas that you should study in this. There are lots of interesting ideas, and the kind of creative techniques people have used in past, just amazing. Okay. Now, question to all of you. So ChatGPT is a classification. Okay. Why? Classification. It classifies the input sentence into one of the words. At one time, it produces one word or sometimes one letter. Okay, some models give one word at a time, some models give one letter at a time, and some people have chosen a mid path, like produces one syllable at a time. Okay, so ChatGPT is a classification. It classifies input into one of the words. Okay, because it produces one word at a time. Okay, the output, we am calling it class in which it's classifying. It's producing one word at a time. I'm calling it, it classifies the input into one of the words. Okay. The loss function that it uses is that of a classification. We'll talk about the loss function that we use in classification very soon. Okay. Now, we heard generative AI, the one that generates images. Okay. A model that generates an image. Is it classification or regression? Now, this is hard. Okay. Even the researchers who worked on this problem, they tried everything, and then they finally reached to a conclusion that generating an image is, I'll give the answer soon. Yeah.
I mean, won't it be regression? The reason again is predicting the red, blue, and green coordinate for that particular pixel.
Okay. Anybody else wants to take a shot?
I think if we look at the final outcome, we want to say whether it matches the picture or not, right? So you should get.
No, there's no matching the picture. It's just producing image.
Producing an image.
Yeah. It is creating image for you. You type a prompt, it generates an image. Okay, go ahead. Let's say even if we are matching, so what?
If it is matching, then it should be classified. It should be treated as classification. That's what.
It's not one class. It's not one class. It creates all kinds of images.
Yeah, but there would still be some finite. So are you talking about generation or matching?
Generation.
Okay.
I mean,
If
it
it was
will.
matching, if it was matching, I know that the answer will be classification clearly. But
No, but Sandeep, thinking out loud, right? The generation part is definitely a regression because you have to understand what that pixel will be. But to match that word to what you need to generate, that would be classification, right? So if you say ball, the red part needs to go to red and the ball needs to go to some kind of ball, right?
yeah,
A round object. So it will be classification, which will go to regression.
the answer is the answer for this one. Your logic is completely correct. Okay, and if and that's what most of the researchers thought, that it's a regression problem, but it turned out to be a classification problem. Okay, yes,
Yeah,
and
so one attempt का marks मिला. Answer wrong है लेकिन answer is wrong, but you get marks for attempt.
yeah, because
crazy.
that's the reality, right? Somebody told me, hey, you don't know what's classification and what's regression. I mean, the one student couldn't answer. Like somebody was telling me that, I asked him that you tell me that in signal processing, if a system is generating voice, like text to voice, is that voice being generated as a classification or regression? And you'll be surprised, that's also classification. The classification model seems to give better results than the one that is the regression one. Okay. So life, it's not that simple. It's not that simple. So don't beat yourself to it. Okay. Those who have not actually built things or have not thought about things, they studied in the book that classification, this regression is this. For them, the life looks very simple. Okay, specifically people with only a bit of academic background. But the reality is that it's not that easy. It's not that easy. Noise cancellation system, when I was building, I was trying to remove the drum sounds from the song. So I had built that thing. And after multiple attempts, I realized that it needs to be a classification. Okay. And that's the important part. Okay, so coming back to this one again. So it is a classification. Each pixel is being classified into one of the categories between 0 to 255. Okay, it's a multi-label classification whereby it's producing so many pixels, so many output labels, and each pixel is being classified between 0 to 255 classes. Okay, that's the way to it. Okay, I can say that, oh, I'm a genius, I knew it earlier, but no. Okay, nobody knows. And as a matter of fact, yes. So, and the other thing I want to tell everyone, that though these things look very cliche and it's a first chapter in machine learning, everybody knows it, right? As of today, but the reality is that the answer is not that easy, and that's marvels me. Like when my teacher was asking that, living, non-living, and for me, that question is always like a very hard thing. Okay, that what's the difference between living, non-living? For many people, the difference between non-living and living is very easy. But when I asked my teacher that, tell me that is a bacteria living or non-living? Okay, so it's not that easy. It might look easy if you just memorize the things, but it's not that easy, right? And then when you read the book by what's his name, Heisenberg, right? Heisenberg wrote a book called What's Life? Okay, and then the physicist actually turns the entire question about what is life, like living and non-living, to be different. So for a primary school teacher, the question of living versus non-living, this classification is so easy, right? They can just say it. But as a matter of fact, that simple question is fairly hard. Similarly, whether a problem is classification or regression, it might look very easy for people, but it's not. It's really hard because you have to keep trying. Now, let me give you another example where, okay, here's a question to all. Okay. There is a model called YOLO. Okay, which which does the image recognition. Okay, we call that recognition. I'll just show you what it does. Okay, just in a moment. Yeah, this one. Okay, ads might come. Okay. So this one, this model that you see here is taking a photo, marking the rectangles here. Is it a classification or a regression?
Classification.
This is a classification.
Anybody else?
Don't tell me it is regression. Whenever we are telling something, you are telling me opposite.
It's
Now that's an important
it's
question. It's neither pure regression nor pure classification. It's both. It's both.
Now you created a third state now.
Yes. That's the important thing. That's the important thing to understand. Okay.
That was out of syllabus.
Yes. I was reading this whole book that Intel has pushed into, like in India, the AI curriculum was designed by Intel. Okay. And they were very clear. The entire book is very clear. What's image recognition and this and that. Okay. And it's complete nonsense. Okay. If I had to, I mean, that's one of the reasons I moved my kid out of that syllabus. Okay. The reason is, it's not that simple. Okay. It might be a good thing to talk about. Okay. But essentially, it's not worth learning that this is classification, this is regression. It's just okay to talk about, but it's not that easy. So if you look at YOLO, right? I want to show you something very important based on going back to your first question. Okay, first question about loss functions. Okay, now here. Okay. All right. You only look once. That was the model's name. Okay. How would a YOLO's loss function look like? Okay. This is the largest loss function I ever saw. And okay. It's a combination of mean squared error and classification. Okay. This is the loss function that you see here. Okay. Do you see the loss function on the screen? Okay. So bounding box is width and height subtracted. So first it's trying to match the bounding boxes, their coordinates, heights, and the probabilities. Okay. So classification and regression combined into the same body because it's a regression. Why? Because it's partly regression, partly classification. Okay, because it is trying to guess the value of the coordinates on the screen, like the XY coordinate and the width of the image and the height of the image. Correct? And then it's also classifying each of the block into an object. Okay, so you can see the most beautiful loss function ever. Right? And yes, the reality is that the entire world uses YOLO as of today for all the image recognition systems. Okay, all the number plates, all the object detections, and so on. And it can be retrained and so on. Okay, so those who are in hurry, they can take a look at the YOLO and You don't need to study YOLO like this. You can just right now just use the YOLO out of the box. It's an open source system. It is probably better than most of the closed source. Okay. All right. Now, I hope you got the picture. Or was I successful in discouraging you in trying to bucket the problem into regression or classification? Okay.
We were about to get confident in terms of understanding, and after that question answer session is
I mean, it's okay. It's not going to harm you in any way. Okay. This lack of confidence is better. This particular lack of confidence. Okay. I used to, right? I used to, worry a lot about those people in my team who would say, I can just judge a person in 5 seconds. Okay. So that's the kind of people I never sent for interviews. So I remember in my team there was this guy who told me, Sandeep, it's so easy. I just look at the person and in first 10-15 seconds I can figure out whether it's worth hiring or not. And I said, you're not going to interview next one. Okay. Because I mean you're fairly judgmental. Yeah. So and you are so proud of your so so what I'm saying is that it's okay to be suspicious. It's okay to be very, very cautious about the model, and it's okay to know this fact when somebody tries to question you in an interview. If somebody is asking you that this is a classification or this, you can always say that the problem can be modeled as a regression as well as a classification. But historically, in these scenarios, classification seems to make more sense and regression does not. Okay, so that would be the politically correct answer. Okay, and if such person rejects you for this answer, it was not worth joining such team anyway. Okay.
Sandeep, how does these, image classification things like YOLO work so fast? Like, yes, detecting is one thing, you can code it, but how you optimize the code actually that it keep running in, pretty quickly, actually tracking every movement. The reason I'm asking there is because, here in Sydney, actually in some of the highways, they put the AI enabled cameras. So they are actually scanning people's car and people activities, like what they're exactly doing in sitting in the car. So I'm also one of the culprits in that. I was holding a burger and driving the car, and they took a photo of me and sent me a penalty of $400 actually. So I'm just, out of curiosity, I'm just checking like how did they able to, track every movement of mine actually, what I'm doing and what not, and then clicks me and send me the right fine. I mean, it's they had a fine. I can show you up actually. It's in my hand. It was accurate but yeah, I mean, my whatever happened, but just want to understand, like, how did that, applications like YOLO work so very fast that it can track every movement of, like, let's say millions of cars going in a highway, right?
Yeah, it took so many researchers. Like YOLO V1 was fairly slow, then second one, third one, fourth one, and the semantic segmentation has been evolving for like 30 years. Okay, so it did not happen in a single day. And if you want my answer in a very like couple of paragraphs, my answer would be that all the fundamentals that we studied on big O notation, they all come in here. Each and every part. Like instead of can I do it on multiprocessors while I'm, let's say, going through one set of weights, when we are tweaking one weight at a time, can I do it parallel using 2 processors? 3 processors, 4 processors? Can I just, quickly do multiple passes? You go through the paper and other things. We'll have the dedicated chapter on this. Don't worry.
Sandeep, I think he wanted next time to skip the penalty that SI is asking of the
No,
equation.
next time I won't be using anything. Like otherwise, if I'll be using it up, my license will be cancelled. I'm running out of the points, actually demerit points. They give 13 points, and I'm already at 10, so just 3 more points left. Next time they'll cancel my license for 2 years.
Oh man. Okay.
Yeah, and here in Australia, they charge hefty penalties. Like even for small mistakes, like you cross a red light, 5 points. You hadn't parked in a correct lane. It's $250, 3 points. So that's how they do it.
Whoa.
Glad
And isn't
I'm in
it
India.
no, and isn't it that if it is a weekend or a holiday, then the penalties
Yeah,
are
in a
more. So it's
public,
like
on a public holiday and weekend, it's double demerits. And in some festivals, like during Christmas, because they know people will be drinking and driving, so they do double demerits and double penalties. Yeah, like I remember, like I've been charged like $1,600 on the day when my daughter was born. I was going to hospital to see my wife, and cross that red light camera. So they click a photo and send me a penalty of that. But I went to court actually and asked to waive off that penalty by putting some emotional justifications on the paper. They finally accepted it up. That's how I've been saved. But yeah, what I'm telling you, penalties are very hefty here. So,
Okay.
yeah.
Okay. No, I think you can experiment a little bit on YOLO and come up with some cases, corner cases, where it recognized your stuff as burger or something, and then you can take them to court.
Yeah.
Anyway,
So
coming back to it.
Those ML algorithms are optimized for revenue generation.
Yeah.
Obviously, these government departments are too rich here.
Yeah. So no, I think in India it requires like full policemen to do it, right? So
Here also now you get the tickets through cameras and all.
I see.
Even the now speeding tickets have also, they've started sending them by auto detecting the speed.
Yeah. So yeah, I think because the thing is, most important part is that YOLO is open source, YOLO is free, and that's why everybody is able to use it. And I think you guys should just take a look at it right away. Don't wait till the computer vision chapter. So as I said, the theme is learn to use the tool, then learn to build the tool. Okay, so we are learning to build all these tools while learning to use all of them. Okay, so I think as a weekly exercise, you guys can just experiment and fiddle around with YOLO. Okay, and I think that would give you guys a good experience. Take a look at their API. Take a look at. You can just download it on your machine. You don't require a server or something. It's not that big a model. It's a small model. Okay, and you don't require like to just use their API and make it run. Just go through their getting started guide and then just launch it on your computer and do it on your Mac or anything. Okay, just start experimenting. And yeah, with respect to optimization, whenever you're building, yeah.
So you said YOLO is for image recognition, right? I mean, is it like we have to use these models only for image recognition, or we can also use this for data anomaly detection or something like that, right? Will it really work, or is it worth trying? I mean, just off the topic. So for example, I got a chance to work on YOLO once, right? But where people are actually using YOLO model for data on anomaly detection, right? Say they wanted to predict, right, whether the data that comes in is it really a valid data or not, right? And then when I happened to read about YOLO, I just got to know wherever I Google YOLO, it is all only about image recognition, right? But people there were really using YOLO model for data anomaly detection, right? And I'm not sure about how or no
What
the
was the
model
data?
worked.
What was the data?
It was just financial data, right? And then they were using for financial data as in whether a particular transaction is a valid transaction or not, right? And then they were trying out using YOLO model, right? Say they were trying to detect credit card fraudulent transactions and all that, right? Say for example, if a transaction is happening, right, and then they wanted to check whether the transaction is an authenticated transaction or not, right?
Nah, they're just misusing the name YOLO. YOLO has got 200 disambiguation on this. They must have just missed it. So see, if you got to build anomaly detection or any such thing, there are better algorithms that are available as part of scikit-learn. YOLO can be used for many other tasks, right? Whether somebody is wearing a helmet or not, somebody is wearing goggles or not, you can retrain it, you can do all of that. But its performance mainly comes from the image recognition and classification. It's a semantic segmentation algorithm. We call it semantic segmentation. Okay, we are breaking the image into rectangles and marking each rectangle with a class. Okay, that's what the YOLO is.
Right,
okay.
Right. Sure, Sunil. Okay, thank you. So in general, right, in general, any image recognition models, I mean, they cannot be used on data, right, or vice versa.
No, in some
Can we
cases,
put it?
it can be like CNN. CNN is a machine learning model that you can train. It's an arrangement to do the image recognition, right? So what people usually do is they convert audio into something called a spectrograph, okay? And we call it mal spectrogram, okay? And then you feed that to a CNN, okay? 1D convolution. We'll talk about this. So people use these models, but YOLO is two things. One is an architecture. Second, it's a pre-trained model combined with some more things. So I don't think it's a wise thing to force fit YOLO elsewhere. Here, you will have to train the things from scratch. Okay. Here, it's already pre-trained model. You don't need to train it. Okay. So it is common to use the model like image recognition model for audio data and so on. It's a very common thing. And those earlier people used to do, right? People would say, I remember some professors telling me, hey, I don't touch audio systems. I only focus myself on CNNs and image recognition. But the thing is, all of these things are interdependent. Okay. And right. So people do use one strategy that they discovered for something into something else. Okay.
Okay. Sure. Thank you, Sunil.
All right. Perfect. Okay, so far, so good. I hope I was able to answer your questions. Now, where were we? Let's start. Where were we? We were in the other folder. Okay. All right. This one, right? Ancient secrets of predictions. All right. Good. So far, we were successfully able to do everything using gradient descent. We built a system for polynomial also, and we did everything. Good. Everybody okay? Now, we also did the quadratic one. So everybody's okay so far. I have done multiple things in the class. And I can also open that, right? So yeah, this one. Remember the gradient descent that we did last time? We did for multiple columns, correct? If you have multiple columns, what will you do? And then we did for squared laws, for polynomial parameters and so on. We did those kind of multiple things. Now, coming back to a very important point. Okay. All right. And also we have done simple curve fitting, line fitting, and yeah. All right. We also talked about the linear approximation. Done. Okay. Now I want to start with something basics, though we have jumped ahead and we have actually coded it. I want to revisit something called a differentiation, or you can say calculus. Okay. So we won't go deep dive. We will only focus on things which are important. Okay. I hope my screen is clear. Okay. In differentiation, we basically compute the rate of change of something with respect to something else. Okay. Or you can say, instead of saying rate of change, a better sentence is we compute the rate of increase of something with respect of increasing some input. Okay. It's also called derivative. The rate of change of distance with respect to time is called speed. Rate of change of speed with respect to time is called acceleration. And like if x is the distance, then and the v velocity of speed is dx by dt. Acceleration is dv by dt. You can think of this as delta. dx means change. Delta x means x2 minus x1, t1 minus t2 minus t1. Okay, so dx by dt, when somebody says x2 minus x1 divided by t2 minus t1. Okay, so okay, the only difference is that this tiny input, okay, the denominator has to be really, really tiny. Okay, the way you should imagine this differentiation is that if there is a function or there is a machinery which takes x as input, gives y as the output, then rate of change of output with respect to rate of change of input is called the differentiation. Okay, here in the denominator it has to be okay partial just okay. So what you see here is dy by dx is basically the rate of change of output with respect to input. Are you guys okay with it? No?
Yes.
Great, great. All right. The other way to look at the derivative is that it's a tangent at a point on the curve. Imagine that this is your curve. Okay. At value x, you got fx. When you increased x to x plus delta x, the y value is f of x plus delta x. And then, meaning when we increase the input by delta, f increased from this value to this value. So f dash x is same as df by dx. And here we are saying this value minus this value divided by this value. Correct? So if you draw a triangle from here to there, if you look at this triangle, this line is the numerator. This line is the denominator. Okay. So the ratio of the perpendicular to base is called the first derivative. Just that this value has to be very tiny. Right? Remember how we did it in code? Yeah.
This line between these 2 points is assumed to be a straight line, right?
Which one? This one.
Yeah, between fx and fx plus delta x, this line.
Yeah. So this basically, right? This kind of is an approximation. Okay. We are saying that when input delta x is really tiny, this thing is going to be straight line, though it's not. Okay. We are just saying that It's kind of a triangle at a very small scale. Okay.
Delta should be so small that it can be treated as straight line without any practical loss, basically.
Yes. Okay. So, a philosophical question to all. Is it safe to say the only thing that is constant in life is change?
Yep.
If the delta is small, yes.
No. Change can also change, right? Velocity is change in distance, and acceleration is a change in velocity. So you never know that right? Okay.
I think the only thing constant is that the possibility of having change. The change can change.
Yeah, but that's also not constant because
And the possibility of having
exponential
change is always one, right?
Okay, yes. But sometimes the change itself is exponential. So rate of
Yeah,
change
the
of
change.
exponential, like the way virus was spreading, the coronavirus, COVID, was spreading, the rate of change of virus was also exponential. Okay.
So rate
Yeah,
of
I
change
mean,
is also
the rate of change and what exactly changing, all that can change, but the probability of change will always be one. So that is constant.
Okay. You are saying the meaning of this sentence is constant. Is that what you're saying? The meaning of this sentence is constant.
Yeah, yes.
Okay. Okay. All right. All right. Okay. That I agree with you. Okay. Perfect. Okay. So essentially, if you see the rate of change here, you can see the slope, right? It's changing as you are progressing on this curve. Okay. All right. Now, okay. So, all right. Let me help you revise what was differentiation about. Okay. So if y equals to constant, let's say 10, dy by dx will be
0.
okay. Can you prove it?
That is something you have to self.
No, dy will always be 0, right? The change,
No,
because y is
differentiation of a
constant, so dy
constant.
will always be there.
Yes. So no matter what is the denominator, let's say we change denominator to from 5 to 10, the y will always be constant. So dy by dx is 0. Cool. Everybody okay with this? We are going first principle. Okay.
Yep.
All right. All right. Let's say take a look at right. I just make a note of these things because I know that most of you have lost touch with basic calculus, but it is not that difficult. But it's good to look at the calculus from different angles. Okay. Now this is clear. Now if y equals to 10x, okay, how much is dy by dx? Go ahead. If y is 10x, how much is dy by dx?
That should be 10.
10.
Okay, now prove it.
Because no, so it will be 10 into x2 minus x1, right? And so whatever the value of x is.
Okay. Yeah, let's do that calculation. Okay, so let's say our x went from x, right? Initially, x plus delta x minus. This was initial, final. This was initial. We increased x to x plus delta x. Okay. Now, how much will this become new? The y will become 10 of x plus delta x minus 10 of x. Correct? At x, how much is y? 10x. At x plus delta x, how much is y? 10 times x plus delta x, right? So this will be, everyone, this will become, this 10x will cancel this x, and then you'll have 10 of delta x divided by delta x. Delta x cancels, we get 10. Everybody okay with this?
Right. Yes.
This is extremely important for everyone. You have to know the first principles, okay? You cannot afford to say that I memorized it, okay? Because we have already coded it, right? We have already wrote the code to compute the differentiation, okay?
This is called as first principle.
Yeah.
First principle of differentiation.
These are first principles in the entire philosophy, that when you don't know the formula, what do? You start with definition. Okay. When I don't know the formula for something, if somebody gives me a if-else condition or some kind of a complex code, when I don't know what I'll do, I will just start with basic first principle. Just go with the definition. Start from zero. Okay. All right. So yeah, now if y is equal to x square, how much is dy by dx?
Be 20x.
That's 2x.
X.
2x.
That's
Okay.
2x.
2x. Let's try to derive it. Okay. Numerator. So what we have to do? Y2 minus y1 divided by x2 minus x1. Correct? Which will be, if let's say initially it was x, finally it became x plus delta x. Numerator, how much is y? How much is y at x square? How much is y at x plus delta x square?
X plus delta x the whole square.
X plus delta x whole square. Okay. Let's expand it. The numerator turns into 2x delta x plus delta x square. And denominator is delta x. Delta x cancels out. You get 2x plus delta x. Is everybody okay with this? Right? So the answer is 2x plus delta x. But since delta x is really tiny, we ignore it and we say it 2x. Okay? Are you guys okay with this? Good?
Yes.
Yes.
Sandeep,
Yes.
why we are saying delta is too tiny though? Like, difference can be big or large. I mean,
No, that's a definition. So when we say derivative means compute the ratio of change, and the change has to be really tiny.
okay.
Okay. Yeah. All right. This change at the value of x, we are saying that, all right, we are not saying it's at x plus delta x, correct? Because here you might say that, okay, this triangle that we just drew, it looks crazy because you are saying this is a rate of change at x, but no, there is x plus delta x. Why are we saying it's on x, right? You are saying rate of change of y with respect to x at x. But it's not. It's basically x plus delta x. The answer is, since delta x is really tiny, it doesn't make much difference. So we basically ignored this delta x. Okay. That's a definition. So basically the entire definition is when you see in formula, when you see the moment, the reason basically when I was studying in CBSE, in the first time I encountered this, the one thing I hated was this symbol. Okay, you see this thing? This?
Yes.
That's what actually caused a lot of confusion in my head. Okay. Then I don't know what it is. So actually in CBSE, I skipped the limits chapter. Okay. It's when I had to prepare for JEE, I had to go back and study the limits chapter again. Okay. So yeah, just because of this symbol. Okay. Because some people said
Okay.
LT, X tends to 0, delta X tends to 0. Somebody said this. Okay. While the reality is that this is a pretty simple thing. It's a rate of change. Okay.
Yep.
All right. Is everybody okay so far? If somebody gives you a formula or anything for that matter, let's say somebody gives you, okay, wait, what happened to my screen? Okay, never mind. I'll just try to write this. Okay, so let's say you are given now 10 of x of whole square. Okay, right? Okay, so right, this is where you remember the chain rule. Chain rule is that first consider it like a big number, like you can say, if you are given y equal to capital X square and x is equal to 10 of x, you compute delta y by delta capital X, which comes to be 2x, and then you compute this by small x, that comes to 10, and then you multiply these two things, delta y by delta capital X, small x equals 10 times 2 of capital X, which is 10x, and it is equal to 200x, and this get cancelled, so dy by dx is 200x. You see the chain rule? How would you derive the chain rule? Remember the chain rule? So I've just tried to derive the chain rule for you. No?
Chain rule.
Yeah, chain rule.
Okay.
Chain rule, remember that whatever it is, we usually say, okay, whatever is there in the brackets, just do it twice of 10 times x, and then times inside. That's how you do it. Okay. So the way to solve such problems is that if you know the formula, we just derive the formula of x square. Okay. So we know that if something is squared, what to do with that. Okay. And right. And we also learned that if something is multiplied with 10x, that one is 10, and this one is 2x. Now we multiply the two things, and this dx from both sides get cancelled, and you get the answer. Got it? No.
Oh, so this chain rule means, is it something that was taught over here? Means we did it in the class, or it's like from our old maths concepts?
It's all old maths concept.
Oh, okay. Then I must have bunked that class.
Sandeep,
Yeah.
how it is 200x? It is 2x and 10, right? Then it's 20x, right? How
No.
come?
Oh, yeah. No. It'll be, see, if something is squared, what do? Twice of that something, correct?
Yes.
Multiplied with whatever is the differentiation of that thing, which is 10. So 200, right?
Okay, okay.
And now let's right, the way to think of it is this. Okay. If we give it a name, say capital X, so we
Okay.
say dy by d capital X is 2x. We just derive the formula, how it is. And then capital X is equal to 10x. So d capital X by dx is 10. Okay. So this is twice of capital X, and this is 10. So this becomes twice of capital X, which is twice of 10 of small x, and that's it. Are you guys clear?
But then why can't we solve it with like the regular formulas, like 10x? So with the delta x, we substitute that and then solve that equation.
Yeah. You
We
can
can,
easily, you'll still get the same answer.
same answer. Okay.
Yeah. Okay. All I'm saying is, since we already solved it for 10x, we solved it for x square, we just used that. Got it? So,
Oh, okay. Got it now.
okay. Yeah. So if you can break down your formula into something that you already know the formula for, we know y equal to x square's first derivative, and we know y equal to 10x. So that's it. We can just utilize it by using the chain rule. Okay. Like if I ask you, what would be if y is equal to 10 of x plus 10 whole square, okay? And then the whole square, right? Okay, then the whole square, what will be the answer? Okay, so you can write it like y equal to y1, or let's say a square, a equal to let's say b square, and b is equal to 10 of x plus 10, right? And then you can say dy by dA is 2a that we have already studied. dA by dB is 2b, and dB by dx equal to 10. And then we multiply it. So dy by dx is equal to 2a times 2b times 10. And let's substitute how much is a. A is equal to 10 of x plus 10 whole square times how much is b. B is this, so which is 10 of x plus 10, okay, and into 10. See that? So this way you can essentially break down lots of problems into this. And if you don't know the formula, just apply the first principle and solve it. Okay. Everybody okay?
So the last question that we solved, 10x square one, do we really need a chain rule for that? Because 10 would be treated as a constant and we would be only differentiating x square, right? So it should be 20 x.
No. So 10, if it was outside, then it's okay. Like here, it's okay to delete 10, right? But here, 10x plus 10 exists, right? I mean, we can't just say that this is equal to the differentiation of 10 of x to the power 4. That will be simply 4 times 10 of x cubed times 10. Okay, that's not same. Is that what you meant?
No, so I was asking about the previous question that we just solved.
Okay.
Y equals 10x square. Is it the same one?
No, there's a 2 squares on top. See?
Oh, okay. No,
There's
I
one
was.
more. There's one more square here. So yeah. So if we remember the previous one, we could just use that one without any hesitation. All right. So yeah. So what we see is that if we know how to compute the differentiation of something, we can just use that formula in this manner. Okay. And those who are wondering, like, how come I remember the differentiation so well, even today? The thing is, I wrote a analytical differentiator as one of the challenges. Okay. So in which, given any sine square, cos square, x, all of this, my code would basically differentiate it. Okay, it will load it as a tree and then compute another tree and then prints it out. So that's what I had done long back. Okay, so because of which I ended up becoming very good at the analytical differentiation. We call it analytical differentiation or algebraic differentiation. Okay, now, so I hope this is clear. Now, where do we use it? That's
exactly.
Okay. Question is, why do we care about this? Okay, where can we use it? Okay, the first example is this we have already done. Yeah. Okay, so the purpose of differentiation is basically finding the minimum value of a function. Okay, if you pay attention to this movement here, pay attention to what happens when it reaches the top. When it reaches the top, what happens to the differentiation? Yes? What happens to gradient at this point?
Zero.
Zero, right? Okay. So that's a very important quality to observe, that at minima or maxima, the gradient is zero. Okay. Now, notice the second derivative. What happens at the bottom? The rate of change, what's happening to the slope? Slope is changing from negative to positive, right? Slope at the bottom is changing from negative to positive. Are you clear with that? And at the top, slope is changing from positive to negative. Okay? So change of the change or change of slope is negative or positive at the bottom. Here, the rate of change of slope is negative or positive at the bottom?
Positive.
Yes, yes. So the rate of change of slope is positive, meaning second derivative, rate of change is called second derivative, is positive at small, at the lower end, and rate of change is negative at the top, right? So the general strategy is, if we have to, let's say I ask you a simple question. A simple question is, you are given this function. You are given this function like y is equal to, let's say, 10x square minus 6x. Okay. Tell me the place where it will hit the minima or maxima. Okay. What is the minimum value of this? And at what value of x? At what value of x y will be minimum or maximum? Yes? How would you find out? What's the first derivative of this? Dy by dx is how much? Okay, 10 times of x square, 2x.
20x minus 6.
6. Okay, so which is same as 20x minus 6. Right? We are saying that at maxima or minima, this thing is going to be 0. So x will be 6 by 20, which is 0.3. Right? At 0.3, this will be 0. Correct? At 0.3, this will be 0. Are you okay with this? We just found that at 0.3, it's going to be 0. Now, how do we know it is a minima or maxima? We do the second derivative of this. Okay, so we do the second differentiation of this one. So when we differentiate this again, what do we get? 20. this is positive. What does it mean? What does it mean? If the rate of change is positive, is it minima or maxima? You just said it.
Minimum.
Minima, right? Okay, let's just draw this curve and observe it. Okay, let's just draw this curve and observe this. Okay, what was that? Desmos calculator, right? What was the name of the function that we just rubbed off? It was y equals to 10x square minus 6x. Okay, let's take a look at this equation, right? So you see here, do you see that? At the minimum, it's hitting the minima as 0.3. Correct? You guys can see it?
Yeah.
So using differentiation, if we know this equation of something, using differentiation, we can find that minima point quickly. Right? So if we have to minimize loss, and if we differentiate the loss with respect to parameter and equate it to 0, we should be able to find that minima point. Correct? So whatever calculation we did was simple. We differentiated y with respect to x, equated to 0, and we found out that for x equal to 0.3, we would reach the minima. And when we plotted the graph, we were right. Isn't it? Okay, so using this technique, a lot of algorithms are designed. Okay, one of the algorithm that I want to talk about is ordinary least squares, or we call that normal equation. All right. Okay, I have talked about these cases. I also have talked about the chain rule by doing that. Now, right? You can try the multiplications, and this is a good example. Okay, now we talked about the finding minima and maxima. Okay, right. So what we do is we will right from here we'll continue tomorrow. Okay, say right. Yeah, this one. Okay, this one. Now we had an equation earlier, right? There were three equations that we had been going through from the beginning. Where were the three equations? Yes, this is our error. Okay, this is our error. Okay, this is our error function. We assumed mx plus c to be our state line. We put it into the first point. We got this much error. We squared it. Then we summed it with the error due to the second point, third point, and the overall error is this. Okay, so very simply, if we do dE by dm equal to 0, dE by dC equal to 0. And if we solve those two equations, we'll get the value of m and c for which the error is minimum. Okay, so we'll continue from here tomorrow at the same time. All right. I just today we brushed up on the calculation and of differentiation, and we will continue from here. I hope this is not bad. All right, everyone. Have a good day.
Thanks, Sandeep.
All right. Okay.
Hey, Sandeep, can you check in the...
Oh, yeah. Thank you so much for reminding. I will, in presence of everybody, I'll just do it right away.
Proof.
Before I forget. Okay. Yeah. All right. Let's just do it. Okay. So status. Git add August 23. Okay, Git commit. Okay. All right. I think this is all right. Did I miss anything else? No. Perfect. We will talk about it. Yeah.
Yeah.
And
Sandeep, I may need your 5 minutes tomorrow, maybe before class or after class, just to talk to you around something around data classification
okay.
requirements popping up in my organization actually.
All right. Instead, just ping me on WhatsApp. I'll just give you my calendar and we can have a conversation.
Okay.
Cool.
Okay, sure.
All
Okay,
right.
yeah.
Have a good day, everyone.
Yeah.
Thanks all. Thanks.
Thanks, Sandeep. Bye-bye.